Hi, in this video we're looking at the normal distribution and the inverse distribution. And this all began with a mathematician named Karl Gauss. Okay, so think of mouse, take the M off, and you have Gauss. And he was one of the first to look at the distribution of, it could have been anything, and realize that it formed this bell-shaped curve, which we're going to concentrate on. So for example, if it was just 100 men, and we took the height of those men, then in the middle, you'll notice the frequency. There are a lot of men who are in this, let's say, from about 165 to 172. In this area here, there are a lot of men in the middle of the bell. The frequency is much higher. And then towards the edges, we see that we have very few men out here that are 100 and over 100 and, can't even read it, 95 centimetres, or down here at 160 centimetres. There are just a few men down here and a few men down here that are very tall or very short. Most are in the middle. And Gauss discovered that this bell-shaped curve is true for many, many things, mostly natural statistics that you find. This is weight, say the weight of year 9 students, or year 10 or 12 students. You'll find in the middle that most students weigh between 65 and 90 in the middle, but there are a few on each end who weigh a little bit more or a little bit less. Now, as the sample size increases, this curve will smooth out. You can see it's a little bit higgledy-piggledy up at the top there. It goes outside of the curve. Well, that will smooth out. This is a spectrometer, some kind of chemical, and the absorbance. The frequency, how many pieces of metal have this absorbance, forms a bell-shaped curve. The last one, even something like gold prices. On the day-to-day fluctuations may fluctuate a little bit. The gold price goes up a little bit or it goes down a little bit, generally stays in the middle. Now, as I said, with a small sample, the bell-shaped curve it goes up and down somewhat. This is a sample of 1,000. The next sample down is 10,000. And then we get down to 1,000,000, a sample of 1,000,000. So if this was, I know we could take the heart rate of 1,000 or 1,000,000 students, you'd find that you would get a much smoother curve with the bigger sample. You've got a lot of scores in the middle here, a lot of rates in the middle, or whatever you're measuring, with just a few on either end. We'll notice that this curve is also symmetrical, and that the middle value here is the mean. Because it's symmetrical, the median and the mean are the same, and the mode would be the most common, and so that is also in the middle. And we use these values that 50% of our population is on one half, 50% of that population is on the other half. Now, this is an important diagram that you need to actually memorize. In the normal distribution, with like a perfectly shaped normal curve, then we can divide it. The first line that you put in is the one down the middle, and this we give the letter M, the Greek M, which is mu, like a U with a tail. And that's always that middle value, the mean. Could also be the median. And then we divide the rest of our graph into 3 on each side, 1, 2, and 3. each of these divisions we call a standard deviation. You can divide the other side into 3 also, 1, 2, 3, and those are standard deviations. Now you need to stop the recording here and copy this down and write down each of these proportions, that it's 34% in this. This is one standard deviation. Okay, the word standard deviation. Standard deviation. This area in here is one standard deviation. And you'll come to see what that means. It's just a way of dividing up this curve. The second part here, this is 2 standard deviations and 3 standard deviations. Okay, so if I take the middle area of the curve here, it looks like most of my population is within that red shaded area, and that would be 68% of the distribution is within that one standard deviation of the mean. And the total area, if you add up all the percentages as decimals, it becomes 100 out of 100. At the ends here, it doesn't quite touch. When you draw these curves, it doesn't quite touch the end because we're never sure what the most extreme values will be. So looking at this again, we can draw the curve, a quick sketch of the bell-shaped curve. We know that 68% of the data, like we just drew, is within one standard deviation of the mean. And we also say that's likely. It's likely that students will be between this height here and this height here. Okay, it's likely. Let's use a different colour. Let's go to purple. It's very probably or very likely that students will be between these weights or heights. Between those purple ones, it's very likely that students will be between those 2 weights. And if I take a third colour from the third standard deviation here, the orangey colour, it's almost certain that students will be that weight or that height, or that leaves will be that weight, or that the lambs will be between the weights, shown within 3 standard deviations, that orange area. They will almost certainly be there. Okay, so a standard deviation, we actually don't need to work this out. We used to do this in statistics, finding x and the mean and the difference between those, and this complicated kind of little equation we had to do for all our data. But now we just mostly use a calculator to work it out. So the standard deviation, the symbol is an S, or the Greek S, sigma, which is, I haven't drawn very well. The Greek sigma is a kind of a circle with like that. Circle with a bit on top is the S. Okay. Given an example of 2 different standard deviations. Both of these populations, the red and the blue, both have a mean of 100. You can see down the middle there, the mean is 100. But in the red population, if you divide it into 3 parts, you can see it's very narrow parts, and that standard deviation is only 10. Whereas the blue, my standard deviation, if I had from the mean and I divide that into 3, my standard deviation is 50 for each. You'll see how that... Okay, so when we do these problems, let's have a look at this one. The best thing to do is to draw a sketch. Let's draw a sketch here. Just draw a bell-shaped curve. Our mean is down the middle. In healthy people, body temperature is normally distributed. So we know that it's a bell-shaped curve because it's normally distributed. The mean is 37.4 and a standard deviation of 0.2. So that means I can divide this side up into 3. My drawing's not very accurate. Into 3. And I'm going up by 0.2. Each of these sections I add on 0.2. So this next one is 37.6, 37.8 and 40. Going down, I'm 37, I take off 0.2, 37.2, 37 and 36.8. Because I know that the mean here was 37.4 and each deviation or each section I'm going to add on 0.2 or take off 0.2. And the question is, what percentage of temperatures lie between 37 and 38? So that shaded area is 37 is there and 37.8. So that's 2 standard deviations. And we know from those measurements we took before, if we have 2 standard deviations, each side of the mean is 95% probability. So 95% of temperatures lie between that. What about if we're looking at, I'm going to rub all this off. Oh, whoops. Didn't mean to rub all that off like that. What about the next question? What percentage of temperatures are less than 37? Well, there's 2. Okay, so 37 is in this section here. And that's less than 2 standard deviations. I know this half of the graph is 50%, and I've taken off 2 standard deviations, which is 47.5. So I'm left with 2.5%, or from your other percentages you can see that that red shaded area, the temperature being less than 37 degrees, there's a 2.5% chance. Okay, the next one, we always draw the curve. So if we draw a curve here, and we're given the mean usually, the mean is 10, standard deviation is 3, so I'm going up 1, 2, 3, this will be 13, 16, 19, and then I also go down by 3, 7, 4, 1. And I'll just do a couple of these questions. What's the probability or percentage, sometimes they'll ask for percentage, sometimes probability, that x is between 7 and 13. So there's 7 and 13. That probability, remember, is 34 and 34, 68%. That the probability is greater than 1. So I just have down here is 0.5%. So greater than 1 would be everything but that red shaded area there. So it would be 99.5%. Okay, and you can continue to work those out. Okay, I'll stop that there and we'll go on to the next video and look at how we use our calculator to work out these probabilities.